Welcome to the deep dive. Today we're taking a really fascinating look, a deep dive into something super important if you're designing or even just trying to grasp complex energy systems. We're talking about the diagnostic warnings from this powerful modeling tool, EnergyPLAN, our mission, to unpack what might seem like, just technical errors and turn them into actual insights about building energy systems that are, well, robust and resilient.
Exactly. And they're not just error codes, not really. Think of them more like sophisticated feedback. They really pinpoint potential weak spots or inefficiencies, or sometimes just fundamental physical limits in a design. They kind of force you to confront these practical interdependencies, things that are honestly quite easy to overlook otherwise. And the tool makes them pretty obvious. You see them in the input tabs, lower left corner. They're on the output prints and right there at the top of the output screen too. Hard to miss.
Okay, let's get into it then. We have this list of specific warnings from EnergyPLAN. We'll go through them, figure out what causes them, but really, what's the bigger picture? What do they teach us about designing these systems properly? Let's maybe start with the heart of it all, electricity supply and grid stability.
Right. So the first one you might run into is critical excess, or CEEP. This pops up when your system, for at least an hour, maybe more, is producing more electricity than your outgoing transmission lines can actually handle. It's a hard physical limit. If you can't get the power out, the system, well, it just can't operate like that. The key thing here is realizing generation isn't enough. You have to plan for getting the power out and managing it flexibly.
Yeah.
It really shines a light on that link between how much you generate and what your grid can actually take. Pushes designers to think about flexibility, maybe curtailment right from the start, especially with lots of renewables. In the tool itself, you can activate CEP strategies. They're in the balancing and storage section, or you can just let it calculate how big the excess is to understand the scale.
That's a great point. Electricity just piling up with nowhere to go. So beyond just flicking a switch in the software, what's the design lesson? Does CEP sort of naturally push you towards more flexible demand or maybe storage, especially with wind and solar being so variable?
Oh, absolutely. It's a direct nudge towards thinking about system flexibility. If you can't send the power out, you've got to either use it locally, store it somehow, or, well, dial back the production. And yeah, it's super relevant now with more intermittent sources like wind and solar. You get these big surges of power sometimes, and the grid needs ways to cope transmission, storage, or, like you said, flexible demand.
Okay, so it's not just the amount of power, but also its characteristics, how it flows.
Right.
What if you technically have enough power, but it's not the right kind for the grid?
Well, that leads us nicely into the grid stab. Problem warning. Grid stability problem. This one isn't just about quantity. It's about quality and stability. It flags when the system isn't meeting the requirements you've set for grid stabilization. Often this means not having enough share of electricity from what we call active units.
Active units.
Yeah, things that can actively help stabilize the grid, provide regulating power, inertia, that sort of thing. Traditionally, that's large CHP plants, big power plants. Those are usually assumed to have these capabilities. But, and this is quite neat, you can actually tell the model if your smaller CHPs or even vehicle-to-grid setups.
V2G, right, where cars feed power back.
Exactly. Or even wind power, if they also have these stabilizing abilities. You specify that in the balancing and renewable settings. This warning really underlines a big shift, doesn't it? It's not just meeting demand anymore. It's about ensuring the grid stays stable, the quality is there, especially as we move away from those big traditional spinning generators.
That's a really crucial difference. Are there common misunderstandings about grid stability? Or maybe surprising ways to tackle it beyond just the old spinning reserves?
Yeah, a common one is thinking that just adding more solar panels or wind turbines automatically solves stability. It doesn't, not directly. They add energy, sure, but traditional grids relied on the physical inertia of those massive turbines. Modern solutions. They might involve things like advanced inverters on solar farms, grid-scale batteries that can provide synthetic inertia, or even really smart grid controls that adjust things dynamically. This warning just makes sure designers don't forget that piece.
Makes sense. Okay, and what if you're planning to lean on importing electricity from elsewhere?
Well, then you might hit the PP import problem, power plant import problem. This basically signals a bottleneck coming in. Your electricity import for 1 or more hours is trying to exceed the capacity of the transmission line bringing power into your system. So even if you have an agreement to import power, the physical wires have limits.
Okay. Like a traffic jam on the energy highway.
Pretty much. And the solutions are fairly fundamental supply-side stuff. Either you need to boost your own internal generation capacity, build more power plants, for example, or you invest in bigger transmission lines coming in. It flags that infrastructure bottleneck very clearly.
Got it. These electricity warnings, they really do show how tangled everything is. Generation, storage, transmission. It's not just about flipping a switch. But energy systems aren't just electricity.
All right. What about other carriers? Do we see similar warnings there?
We certainly do. Take the biogas shortage warning. This pops up if your annual demand for biogas or syngas, that's synthetic gas, often from biomass or waste, if that demand is higher than what you've configured as your supply, you set those in the synthetic fuel and biomass conversion tabs. It's a straightforward mismatch. You either need to plan for less demand for that specific fuel,
Or make more of it.
or figure out how to produce more, exactly. It really brings home the need to balance fuel production and consumption. Makes you think about, resource availability, supply chains for those specific fuels, right? Like making sure you have all the ingredients for your energy recipe. What about transport? Especially with EVs becoming so central.
Good question. For that, there's the V2G connection too small warning. This one's pretty direct. If the connection capacity you've specified for EV charging or for V2G, if that's not enough to handle the electricity demand you've put in, you get this warning. Solutions are, again, quite practical. Either reduce the charging demand in your plan or spec a bigger connection capacity. It points to those very real infrastructure limits right at the endpoint.
Okay, and heat. District heating comes to mind.
Yep. And for that, we might see DH boiler capacity is too small. District heating. This means your district heating system could be a big central plant, or smaller local ones just can't meet the peak heating demand. It highlights that need for enough peak capacity, for those really cold snaps.
Yeah, you don't want the heating failing midwinter.
Absolutely not. This warning flags that potential shortfall early. Solutions. Add more boiler capacity. Maybe look at reducing peak demand somehow, or perhaps boosting other heat sources in the system if you have them.
It really seems like a running theme here. This mismatch between supply, demand, and the pipes or wires connecting them. It's not always obvious how one part affects another, is it? The model seems great at pinpointing those specific choke points. Thinking about future systems now, hydrogen is a big one. What kind of warnings or challenges pop up there?
Hydrogen definitely brings its own set of considerations, and one warning is quite unique: electrolyser increased. Now, this isn't strictly an error, it's more informational. What happens is EnergyPLAN sees you need more hydrogen than your specified electrolyser capacity or imports can provide, so it automatically increases the electrolyser capacity in its calculations to make the system balance.
So it fixes the problem but tells you it did.
Precisely. The warning is there because you, the user, need to know this happened. Because that increased capacity means increased investment costs. It's a flag saying, hey, the model assumed more investment here. You need to check this and factor it into your budget. It's a really important reality check on costs and feasibility.
That's clever. So it highlights hidden assumptions that have real financial impact. Okay, what else for hydrogen?
Well, then you have warnings like transport electrolyser is too small. This comes up if the hydrogen demand for transport, or maybe for industrial processes like hydrogenation, if that demand isn't met by the production capacity and storage you've defined. And storage is key here. You set that up in the electricity storage section, actually. Adding hydrogen storage can often reduce the peak electrolyser capacity you need because storage lets you smooth things out, produce hydrogen when power is cheap or plentiful, and use it later.
Right, storage acts as a buffer.
Exactly, and it's the same idea for the NDV. CHP electrolyser is too small warning. This applies if you're using hydrogen for individual micro CHP units, maybe in homes or buildings. Again, if the electrolyser capacity isn't enough for the hourly demand profile, hydrogen storage can significantly help reduce the required peak capacity by balancing supply against that variable heat demand. It shows how storage is crucial for hydrogen, just like for electricity.
Okay, so capacity and storage seems to be the mantra, especially for these newer energy vectors like hydrogen. But you mentioned one more warning, something a bit different. That's about the data we actually feed into the model.
That's right. It's the negative L demand warning, negative electricity demand. This happens in the electricity demand setup. If you have, say, electricity demand for heating or cooling, and when the model subtracts that specific demand from your total electricity demand hour by hour, it results in a negative number for some hours.
Negative demand. How does that happen?
It usually means there's an inconsistency in how the annual demands and the hourly distribution profiles have been set up. Maybe the profile for heating demand is higher in some hours than the profile for total demand allows. The model is smart enough to fix it on the fly. It just sets those negative hours to zero. But the warning appears because now the total annual energy calculated won't quite match what you intended based on the inputs because of that adjustment. It's a fundamental reminder about data quality. You need carefully designed, consistent inputs, annual figures, and hourly distributions to get accurate results. Classic garbage in, garbage out, really.
Wow. Okay, so we've walked through quite a range here, from critical excess power flows to grid stability needs, fuel shortages, hydrogen infrastructure, and even down to the input data itself. It's really clear these energy plan warnings aren't just annoying error messages. They're incredibly powerful diagnostics. They reveal that complex dance between supply, demand, storage, and infrastructure.
They really are profound teachers, I think. They demonstrate that a successful energy transition, it's not just about hitting some big annual generation target. It's about making sure every single piece, generation, transmission, fuels, end-use demands is balanced and works together hour by hour throughout the year. They challenge us, force us to think critically about every assumption, every connection, to take that holistic view.
Absolutely. So for you, our listener, maybe here's a final thought to take away from this deep dive. When you look at any complex system, an energy grid, sure, but maybe something else entirely, what kind of warning messages should you be looking for? What seemingly small detail, what little inconsistency might actually be pointing to a much deeper fundamental issue that could affect the whole thing? Something to think about.